Hello everyone. We will continue studying one-way ANOVA today. And so here the basic setting is we have m different groups. So this is the first group and the second group and the third group. So each group will give one sample which is composed of these four example or four observations. So in this case we have three groups where m is 3 and then n is 4, which means in each sample we have four different observations. And so as I mentioned, we want to test whether the true mean parameter for each group. So each different group were given a different brand of milk when they were grown. For different different children, and then depending on this different milk, their average height might be different or not actually different. So we want to see if different milk has a significant effect on a person's height. And so our initial hypothesis was H not being mu1 through mu m are all equal, which means that the true mean values of all these groups are actually the same, and H naught or H alternative is this one is not true, which means that at least one group has a different true mean value from the other groups. So in order to do so, we first computed some variance kind of measure. So let's see. So in this equation, this one is the individual sample. So if x I being 2 and j being 4, and then it means this sample, okay? And then for each observation. So for each observation, we just subtract its own mean value, which is the true mean value, and then divide it by sigma squared. So here our assumption is even if the means are different among different groups, but their variance are actually the same. So in this case, so if we standardize it in this manner, and then we sum them up for all the individual observations, and then we see that it's following the chi-square distribution with the degree of freedom of n times m. Okay, so the next story was, if we replace the true mean value of mu I, so here we assume that mu1 through mu m can be different. And so for this group, the true mean was maybe 3.5. And in this group, let's see. Yeah, so the true mean was 3.5, and true mean for the second group was maybe 4. And let's see, the true mean of the third group could be maybe 2. So in these cases, certainly H naught is not true, right? Because mu1, mu2, mu3 are different. And so we kind of assume that we assume this situation, and then we subtracted from each, from each observations, we subtracted its own true mean value, and then take the square of it, and then divide it by its common variance, which are all common throughout the different groups from group 1, 2, and 3. So in this case, we understand that it's following the chi-square distribution with the degree of freedom of m times n. And then if we replace this true mean by it's a sample mean. So so xi dot is representing the sample mean of each group. So we can easily compute the sample from 3, 5 to 4, and then that will be called x1i, x1 dot x, and then so the sample mean of the second group will be called x2 dot, and so on. And then if we replace this inaccurate but approximate the sample mean in the place of this true mean value, and then we will have the reduced degree of freedom, right? And so in each group, so in each group we are having a one less degree of freedom from the original degree of freedom. So in each group, so we had a n degree of freedom for this group, right? But in this case, since we replace the true mean by its sample mean, we have a one less degree of freedom from n, and then we have m different groups, right? So we have a 3 groups. Okay, so in this case, we have a degree of freedom of, let's see, yeah, m times n minus m, which is represented in this manner. Okay, so last time we viewed that so the chi-square distribution will have the mean value of the degree of freedom. So the mean value will be, this n m minus m. And so we change, we move this guy in the denominator of the left hand side, and then its expectation value will be the true variance value, or the parameter for the variance. Okay, and so so far the story was this measure called SSW is giving an estimate for our variance value of sigma squared. Okay, so these were the equations that I just explained. And then we now consider the second estimator, or different estimator, for the true variance parameter. And this estimator will only be a valid estimator, or this estimator can only be used when assuming the null hypothesis is true, which means that the sample, the mean value of all the groups are the same, right? So let's look at this second estimator. So in this case, we consider the sample mean from each group. So in this case, we can compute the sample mean of the first group, and then let's see, 5, 10, 14. Yeah, 14, then 3.5 will be the sample mean, which is represented as x1 dot, right? And then what does this sample mean actually follow? What kind of distribution does it follow? It will follow the distribution of the true mean value of the first group, and then the variance as sigma squared divided by 4, because we have n observations within this sample. Okay, so if we standardize this guy in a way that x1 dot minus b1, okay, and then divided by sigma squared over 4, square root of sigma squared over 4, and then this guy will follow the standard Gaussian distribution, right? And then we can obtain another standard Gaussian distribution after standardizing x2 dot and then also x3 dot. And then we basically have three different standard Gaussian distribution or Gaussian random variable. And this is the one that we are using in this second estimator for the sigma squared. So in this case, note that we assume that all the mu i's are equal because we assume that this null hypothesis is true. And so mu1 and mu2, which is shown in the standardization of this guy, right? And so here, let's see, those mu1 and mu2 are all the same, and also mu3 are the same as well. And so we can replace it or represent it as, let's see, okay, yeah, as the true parameter mu, okay? And then this guy will follow the standard Gaussian random variable. And then we basically sum them up for different groups. Okay, so we actually sum their squared value. Okay, and so what I mean is we sum over all the groups starting from 1 to 3. Okay, so this guy will be m in our case, and x I dot, which is the sample mean of the i's group, minus mu and sigma squared over 4, where 4 is n. Okay, and then this guy again is a standard Gaussian random variable. And then we just take the square of it and then sum them up. And then it will follow the chi-square distribution, right? Because each of them is a standard random variable. And then we take the square of it and then sum them up. And then what is the degree of freedom? Degree of freedom will be m, or 3 in this case, right? So we have m degree of freedom for our chi-square distribution, okay? And then if we manipulate this equation a little bit, okay, and then xi dot minus mu squared, and then this guy and this guy will be cancelled out, and then sigma squared, right? And then divided by n, but let's move it to the numerator. Okay, and then we sum them up. Okay, and then we factor it out, all this summation operator, and that way we obtain this guy. And then that will follow the chi-square distribution with the degree of freedom of an m, which is the number of different groups that we have. So again, this chi-square distribution is assuming the null hypothesis, which means for each group, the true mean value will all be the same. Okay, and then we do not know this true parameter mu, so we have to replace it with our approximate value. So in order to do so, we compute this x dot dot, which is simply the average value of all the observations across different groups. Okay, so in this running example that we have, okay, so we basically sum all of them. So 3, 5, 2, 4, and 5, 4, 6, 4, and 4 other values from this group. and then divided by m times n, okay, which is a 12. So we can think of it as an estimator of our global mean value if their mean value were all the same, or this guy was all the common value of mu. Okay, and then from this this representation or expression, we replace this true parameter mu by our estimator of x dot dot, and then this guy will have a one less degree of freedom from the original degree of freedom of m. Okay, so again we had a three different standard Gaussian random variable, right? And then yeah, of course there are sum of squared values, and then we had one single common mean value, and then we replaced it by our estimator, right? And then um, yeah, it will have it will decrease the degree of freedom by one, okay, and then we call this value, okay, we call this value as SS of B, okay, and then yeah, SSB divided by sigma squared, and then this guy will follow the chi-squared distribution with the m-1 degree of freedom, and then we use the same strategy that we used in the previous estimator. So in the case of the expectation value of this, it will be m-1 because the mean value or expectation of chi-square distribution will be the same as the degree of freedom of it. Yeah, and then we replace this guy to the right hand side, and then we move this guy to the denominator of the left hand side. Okay, and then its expectation value will be sigma squared. So the reason why this manipulation is valid, or this manipulation is possible, is because m-1 and sigma squared will all be the constant value. Okay, and so expectation of some constant scalar multiple of a original random variable is just this guy, right? Okay, so from here, yeah, we can divide it by m-1 inside of this random variable, and then in this case m-1 will correspond to alpha, and then yeah, this one is corresponding to this guy, and a is 1 over m-1, okay, and so a times this guy will be just 1, right? And then we can move it to the right hand side as well, because they are just a constant. So we obtain this representation, and thus this guy is also an estimator of our true parameter sigma squared. But again, this one can only be used when this H naught, or the null hypothesis, is true. Okay, so we have two different estimator for our sigma squared. The first one was this one. Okay. So what was this one? So let's recall it. Yeah. So for each individual observation, we subtract its own mean value, or its approximate version of it, the sample mean, from each group, and then take the square of it, and that way we obtain the chi-square distribution. Okay, and from that we obtain the estimator for our sigma squared. And again, in this case, because we assume that different group has its own mean value, and we used their own different sample mean value, and thus this estimator is valid regardless of H naught or the null hypothesis being true or not. Yeah, but in the second case, or the second estimator is only valid when the null hypothesis is true. Okay, and then we can consider their ratio. Then this one is our test statistic. And then because this guy, let's see, yeah, each of these guys are coming from some chi-square distribution, right? And so it can be viewed as the ratio of the two chi-square distribution. And so using this statistic, we will use the DMF distribution, which is the random variable of the ratio of the two chi-square distribution. Okay, and then let's consider, or let's think about which one is larger than the other. So again, this guy is only a valid estimator for sigma squared, but the null hypothesis is true, right? And then suppose H naught, or the null hypothesis, is not actually true, which means the different groups will have a different mean value, or the true parameter of mu i's. Okay, so in this case, from this equation, okay, so this equation, we used the same mu, but in order to make this guy to be standard Gaussian random variable, we should have used mu i's when the null hypothesis is not true. Okay, so in this case, in this example, suppose this mean value, or the mu value, assuming that the null hypothesis is true, although it is not true, but let's see. Okay, so suppose we used this mu, which is the common mean value, in the place of mu1, mu2, and mu3. Okay, and then let's see, in this case, instead of using its own true parameter value of this 3.5 and 4 and 2, sorry, not this one, but let's see. Yeah, so we are talking about this estimator, which is deriving SSOB. So in this case, we should have used its own true parameter value, mu i's. Okay, so which was like, let's see, 3.5. Yeah, 3.5 and 4 and 2 and so on. So if we used its own true parameter value, and then it will still be a Gaussian, standard Gaussian random variable. But instead of using that, we actually used the wrong true parameter as 3.2, all in these different places. And in this case, its variance, okay, its variance of this value will will tend to be greater than the true variance value, because we used the wrong true parameter value of mu. Okay, so this SS of B divided by n minus 1, although this one can be an estimator for sigma squared when all the mean values are true, but if it is not, then this one will be typically larger than this one, which means that this one will be an overestimate. Okay, overestimator overestimates the true parameter of sigma squared. So if we consider the ratio in this manner, then this guy will typically be larger than this guy. Okay, and then if so that way we consider the situation where this guy is only, this guy is larger than this guy but not smaller than this guy. So that way instead of using a two-sided test, we are using just a one-sided test. Okay, and so for our hypothesis testing, we typically start with this alpha value, okay, significance of test. And so if alpha was a 5% chance, and then in our F distribution, so we put 5% probability to the right hand side, because our F measure, or this statistic, will be typically greater than 1, because the again, the numerator will overestimate this true variance value. And then this one will be kind of a proper estimator for sigma squared. So this one will be larger than the denominator. Okay, and so what is our degree of freedom of this F distribution? So if you remember, F distribution had the 2 degree of freedom, and then the first one was the numerator, the degree of freedom of numerator, and then the degree of freedom of the denominator was the second one. And so our F distribution will have these 2 degree of freedoms, okay? And then we are given this fixed alpha value, and then this threshold value will be represented by this, okay? And so this is our test statistic, which is represented in this manner. And then given this value, if this value is exceeding this predetermined value coming from this distribution table or this distribution function, and then we reject the null hypothesis. And then if this value is smaller than this guy, and then we do not reject the null hypothesis. Okay, and then simply we use this degree of freedom of the numerator. We represent it as R, and then this guy as S. So we now represent it as F R comma S. Okay, and this one is just a part of the table of this F distribution. Okay, so this is just nothing but the small part of the table for this F distribution. And then we have, of course, the 2 degrees of freedom of R and S. Let's see. And then also we can compute the p-values as well. So instead of using the predefined alpha value, we used we use this value. And then in our F distribution, again, this guy is our test statistic of this value. So we just compute compute this value from our samples. And then we find the corresponding point in our F distribution with the degrees of freedom of R and S, and then we consider the probability assigned to the right, right? And so this value will be our alpha value. This one will be our p-value. Okay, so we can perform this hypothesis testing by using this p-values as well. Okay, and so this one, yeah, let's look at this example. So we have 3 different groups, and then yeah, we have like 5 different cars within each group, and then it's maybe the total miles that that a car can go by using maybe 1 liter from this gas and this gas and this gas. Yeah, so gas is just gasoline. Okay, and then yeah, so here the number of groups are 3, and the number of observations within each group will be 5. Okay, and then yeah, we can just compute this test statistic that we defined here. Okay, and then here the level of significance is 5%, which means alpha is 0.05. Yeah, and then yeah, we can compute this test statistic and then see if p-value is greater than or equal to 0.05, and so this p-value is less than 0.05, and then we reject the null hypothesis. But if this p-value is greater than 0.05, which means that in this this value, our test statistic was found around here. Okay, so in this case, our p-value will be greater than this predefined 5% probability. Okay. So if this one is greater than this predefined alpha value, the null hypothesis should not be rejected, and thus yeah, we can still conclude that, yeah, we still have to conclude that these different gasolines are not giving a significantly different effect on the total mileages of a car can go. Okay, and then the next part is about this identity of sum of squares. Okay, and so let's look at this equation. So the left-hand side is simply just the squared sum of all the observations across different groups, and then that will be decomposed into this form. Okay, so let's just try to understand this intuitive meanings. So if you remember, if you remember on the regression part, when computing this this coefficient of determination, or what is called is r squared. Okay, so in this case, I mentioned that so I mentioned that so this value, okay, can be decomposed into these 2 parts, and Yeah. Okay, so it's a little hard to explain, but okay. Just let me go back to this equation and then just explain it directly. So it can be viewed as the total energy or some kind of mass that our data has. So it's just a simply squared sum of all the observations. And then it can be represented as, yeah, it can be represented as the sum of the global mean, the squared value of the global mean. And then also this variance term coming from these two SSOB and SSOW. So this one is called a sum of squares, but B is representing the between, and W is representing within. Okay, so what it means is, suppose we have one groups around here, and then another groups around here. So it looks like they have certainly different mean values, right? And then what is their global average or global kind of sample mean? It can be, yeah, so let me just, so we have 6 sample here, and then here we also have to have this 6 sample, okay? And then the left hand side is basically the squared value, sum of these squared values. So if it was a 3, and then it will contribute as 9 because 3 squared. And then the second observations within the first group will be 3.5, and then yeah, 3.5 squared will be contributed or added to the left hand side. Okay, so in this case, we can consider this global sample mean by just taking the average of all these sample, and then it will be represented around here. Let's see, use a different color around here. So it can be represented as x dot dot. Okay, again, x dot dot is the sample mean or just an average value of all these observations from these two groups. So here, we are considering the situation where we have a two groups and each observation, so each sample, we have a 6 observation. Okay, and then this guy is just a sample mean of 12 different observations. Okay, and then what is this SSOB? So let's look at this SSOB again. Okay, so this was the definition of SSOB. So what was this one? So this one was the ice group's sample mean. So we have two groups in the previous example that I just showed. And so we will have xi dot, x2 dot. And then this guy is our global sample mean, right? And then we just take the square of it. And then we have, yeah, we multiply it by n. Okay, so we can represent it, yeah, we can consider it as having, for each group, we will have this term. So if, yeah, so this guy is yeah, this guy is computed m times for m different groups, but it is multiplied by n. So in each group we have n observation. So in the previous case, m was 2 and n was 6, right? And so we have 2 here and 6 here, and then we can roughly think that this term, in total, the number of this term will have 12 different terms in this case, right? But in this case, for each different observations, so again, we have in total 12 different observations, and each observation will have this assigned value, which means so for the first group, so this one is the first group, and this one is a second group. Okay, and then the sample mean of the first group by taking the average of the first 6 observations within the first sample, and then this one will be represented by x1 dot, and then the x2 dot will be around here, right? So this one will be our x2 dot. Okay, and then SS of B, if you remember, then it is taking the square of this difference, okay, by 6 times, right? And for this guy, we also do the same thing. So we are taking the square of this value and then sum them up 6 different times. And then what about this SSW? Okay, SSW, let's see. Yeah, SSW was just a sum of squares of the difference between individual observation and its corresponding sample mean. Okay, and then we just take the square of it and then sum them up over all the individual samples. Let's see. Then for this sample, this value will correspond to, let's see, use this color, like this difference for this sample. Let's see, let me just, yeah. So the same sample mean for the first group, and then this difference and this difference and this difference and this difference and so on, right? And then yeah, we can do the same thing. So we have this difference and this and this and so on. Okay, so we have this side, and this side. Okay, so the meaning of this equation is that, again, the left hand side is just taking the square of individual sample values, right? This guy, and this guy, and this guy, and so on. We consider their squared value and then sum them up. And then this value can be decomposed into, yeah, so for example, consider this sample, okay? And then in this case, okay, so we have n times m, so we can roughly think that this squared value of this value, the squared value of this this amount, or this value, and then also, yeah, and then let's call this one as 1. Then what was the second one? SSOB. And then this guy was this value, right? So this one is the second one, and then this value. So this guy is the third one. So for this sample, okay, for this sample, the squared value of, so for this observation, the squared of this observation can be decomposed into the squared of value of this one, okay, and then the squared value of this one and this one. So if we think of, yeah, like a vector addition, although it's not actually a vector addition, but yeah, again, let's see, yeah, the squared of this value can be thought of as adding the first one. So we moved up to this point, and then we moved up to this point, and then we move back to this point, right? So this is the final position of our individual sample. So so this kind of decomposition is represented by this identity of this sum of squares. Okay. So for each individual sample, we can do the same thing. So yeah, for this guy, the squared value will be corresponding to this, but the global mean is still here. So we go here, and then we go here, and then we go here, right? So this entire value is corresponding to this left-hand side, and then this value will correspond to this value, and then this value, which is the difference between the global sample mean and the the sample mean of the first group is represented in this part, and then also this part. Okay. This part is represented by this guy, which is the square difference of individual sample and its corresponding sample mean. Okay, so this is quite an important identity about this sum of squares. But yeah, we will not prove prove this equation. It's quite tedious, but yep, you can see. Yeah, you can easily prove it, I think. But let's just understand this intuitive meaning in this manner. Okay, and how do we use this equation? So let me show how we can use this equation. So in the case of computing the variance of maybe 3, 5, 2, 4, and then the first one was, yeah, I mean, I'm talking about the sample variance. So when computing the sample variance, the first method was to compute its sample mean, and then 8 and 6, yeah, sample mean was 3.5. And then in this case, we compute this value, 3 minus 3.5 squared, and then 5 minus 3.5 squared, and so on, and then divided by maybe 3. So in this case, we obtain the unbiased estimator for our variance value. But in this case, let's see. The numerator can also be represented in this manner. Sum of xi squared minus n times x bar squared, right? Okay, so in this case, 3 squared, 5 squared, 2 squared, and 4 squared, and minus 3.5 squared times 4. Okay. So this was the one useful identity that we can use. So instead of computing this in computing this measure in this way, we can compute the same value in this manner. So we can use this equation in the same manner. So instead of computing SSB and SSW separately by just following its original definition, but we just compute SSB first and then compute this value and this value. And then in the case of SSW, instead of following the original definition. So what was the original definition? So the original definition was this guy, right? So we studied the original definition of this SSW, but instead of computing this value, we just compute SSW by using this identity. Okay, so that way we can we can compute this SSW a little bit more easily. So this is one example. So we have 3 different groups, right? And so these are the same example that we saw before. Then we can compute these values, sum of all the observations, and then sum them up. And then that will give us the left-hand side of this equation. And then we can compute the sample mean value for each different groups, and then the global sample mean. Okay, and then we can compute this SSOB first by using the sample mean of each group and the global mean. Okay, and then we computed this global mean, and then we can plug this in this place. And then we can easily compute this SSW by following this equation. Okay. Okay. So we first compute the SSOB, and then compute this guy, and then for SSW, we just utilize this this equation, and that way we can compute SSOB divided by 1. What was the degree of freedom of SSOB? It was m minus 1, right? Because it was the square sum of the standardized sample means of different groups. So we have a three groups. So we consider the 3 different sample means like these. Okay. Let's see. Yeah. And then we just take the square of it, and then sigma squared divided by 5, which was our n, right? So we have 5 different observations. Okay, and then each of them were the standard Gaussian random variable, and so we have a 3 standard Gaussian random variable, And then since we replaced the true parameter by the sample mean, which is our global mean value, that guy will decrease the degree of freedom by 1, and so m minus 1 will be our degree of freedom, and then this one will be the SS of B. And then what was the degree of freedom? So we have m times n, right? But within each group, we had this number of freedom, this degree of freedom, because we also replaced the true mean value by its own sample mean for each different groups, right? And so, so n was 5 and m was 3, and so we have 12 here. And so our test statistic is 2.6, and then the F distribution that we have to look for is this degrees of freedoms as 2 and 12. And in this case, if alpha value was used as 0.05, and then this value is 3.89, and then since this value is smaller than this value, so this value didn't exceed or was not bigger than this threshold value, so we should not reject the null hypothesis. Okay. Okay, so among different groups, the gasolines will give the equal mileage or mile per gallon. So that is our conclusion from this hypothesis testing. Okay, and then the remaining part in this lecture is about the kind of a unbiasedness or overestimate. This SS of B divided by m minus 1 is overestimating the sigma squared when the the null hypothesis is not true. But when this is true, this one, the average value of this estimator is this true parameter, sigma squared, but H naught is not true, or the sample mean, the true mean values among different groups are different, and then this one will typically overestimate or give an overestimated value of this sigma squared. Okay, so this is so we understood it intuitively in, let's see, where was it? Okay, 1 second. Yeah. So instead of using its own mu i's, the different mean values or the true mean values, but we just use the same mean value, and so the test statistic, I mean this value, will be larger, or this one will overestimate the sigma squared, right? So in this case, it is showing that, yeah, this is an overestimator for this sigma squared, and these slides are showing the proof for it. Yeah, but I'll just skip this part, and I think you should be able to easily follow them. But I think it's more important to have an intuitive understanding about why it should be an overestimator of this sigma squared, and also, yeah, intuitive understanding about this equation. Okay, so in summary of this one-way ANOVA, we consider this SS of B and SS of W defined in this manner, and then it had a degree of freedom of m minus 1 and n times m minus m, and then in order to perform the hypothesis testing, whether all the mean values are the same between different groups or not, we used this test statistic, and then we used it we used F distribution or F random variable. Okay, so that is the summary of one-way ANOVA, and yeah, that's it for this lecture. Then we will continue in the next lecture. Yeah, we will continue about the one-way ANOVA in an unequal with an unequal sample sizes, and also we will continue to two-way ANOVA. Yeah, thank you very much.